Okay, we're going to cover two sections, section 21.2 and 21.3. 21.2 is capacitors and AC circuits, and 21.3 is inductors and AC circuits. So let's expand the PowerPoint and let's see, make sure, yeah, we're here, capacitors and AC circuits. Let's think about the upper left-hand corner is a DC RC circuit. When you first turn on the power, if you measure the current across the through the capacitor and measure the voltage across the capacitor, you'll get maximum current and minimum voltage right at the beginning. As the current diminishes, it's charging the capacitor, so the capacitor reaches full voltage. The current stops and it becomes fully charged, and so the voltage is maximum. And a similar thing happens in the AC realm. So the voltage reaches its maximum value 90 degrees after the current reaches its maximum value. So the voltage lags the current. So it starts off with maximum current, but you can see it goes down to 0, and the delta V goes up to max right as the current goes to 0, which makes sense. It's fully charged at that point. So the voltage across the capacitor lags the current by 90 degrees. Okay, the capacitive reactance X sub C is equal to 1 over 2 pi FC, where 2 pi F is equal to omega. So you can say the capacitive reactance X sub C is equal to 1 over omega C. Delta V, the voltage across the capacitor, RMS, is equal to I RMS times X sub C. So if you're given the delta V RMS and you divide it by the X sub C, you'll get the I RMS. Okay, now let's go to inductors. We're actually now already in 21.3 inductors in an AC circuit. Here, the delta VL is equal to L delta I delta T. We discussed that in chapter 20. So X sub L is equal to 2 pi FL. So X sub L is equal to omega L, because omega is equal to 2 pi F. Now, so X sub C is equal to 1 over 2 pi FC. X sub L is equal to 2 pi FL. There's no reciprocal as there is in the capacitive reactance. And the delta VL RMS is equal to I RMS times the X sub L. If you're given the delta L RMS, you divide it by X sub L, you will get the I RMS, the RMS current through the inductor. Now, if you recall, when you first flip on the switch, the self-inductance wants to impede the changing magnetic field, and so it actually opposes it. It's current in the negative direction as the voltage is getting bigger. So the voltage reaches its maximum value 90 degrees before the current reaches its maximum value. So the voltage leads the current. The voltage across an inductor leads the current by 90 degrees. And we're going to stop it there. We're going to talk about RLC circuits together.